Good morning everybody. This is another lecture on transistors. Okay, and in this lecture we are going to discuss about the analysis of transistor amplifier. There are two techniques for the analysis of transistor amplifier, and these are number one, graphical technique, and another one analytical technique. Okay, actually graphical technique is used for large signal amplifier and analytical technique is used for small signal transistor amplifier. But in this class I will discuss about the analytical technique of transistor amplifier. Okay, we know transistor is a nonlinear device, but transistor behaves as a linear device when it operates in the active region. Okay, and if we see the transfer characteristic of a transistor, actually variation of the output current, here to draw the transfer characteristic I will use the C mode. Actually we always prefer the C mode for number of advantages. So I will take to discuss the C mode transistor. Okay, and C mode transistor, the output current is collector current and input current is the base current. So the variation of the collector current with input voltage base current for constant Vc is the transfer characteristic, and the variation of the IC with the IB is linear and only in the active region. Okay, so if we transistor is operated in the active region, and suppose this is the linear portion of the characteristic. Okay, so in that region transistor behaves as linear. This is the total region where the transistor behaves as linear, and if we choose the middle point of the linear portion, suppose this is the middle point and it is the operating point, and then apply very small amount of AC signal for the amplification. This is the input AC signal. Okay, thus during the full swing of the input signal, the total operation is confined in the linear portion. Okay, so if we choose the operating point at the linear portion of the at the middle point of the linear portion and apply very small amount to input signal, then we can replace the transistor as a linear device. Okay, and we can use for the analysis the basic laws of electricity. There are number of models for analysis of the small signal transistor amplifier, but here I will discuss about the hybrid parameter model. Okay, and we know transistors are used in a circuit in different mode of connection. There are three modes: common emitter mode, common collector mode, common base mode. But whatever be the mode of connection, always it acts as a two-port network. Let's see, this is the block diagram of transistor amplifier. This is the transistor amplifier. Okay, and there are two loops. This is the input loop and this is output loop, and the terminal behaviors of the circuit are characterized by four parameters. This is input current, this is input voltage, this is output current, and this is output voltage. There are four parameters. Okay, actually this is the instantaneous input current. Instantaneous input current means there are both AC value and DC value. We know the transistor is a nonlinear device, but to operate as an amplifier we have to operate it in the active region. So to operate the transistor in the active region, first we have to bias the transistor in that region. That means there DC bias is required. So for the amplification of transistor, amplification of AC signal, DC biasing is very important. That means for a transistor amplifier there are both AC signal and DC signal. DC signal for biasing and AC signal for amplification. So transistor amplifier have both AC term and DC term. So that the parameters are defined by instantaneous value. And this is the instantaneous current. Instantaneous input current means there are both DC term, and instantaneous value is denoted by small letter with capital subscript, and this is the DC value, and DC value is represented by capital letter with capital subscript and with AC value. Okay. Similarly, input voltage, similarly output also, and plus Vi. Okay. To define the hybrid parameters, among the 4 parameters, 2 parameters, input current and output voltage, are considered as independent parameters. Okay, and rest 2 are input voltage and output current are considered as function of them. So input voltage is a function of input current and output voltage. Okay, and also output current is a function of input current, output voltage. Input current and output voltage are independent parameters, and input voltage and output current are function of them. Okay. Now, making the Taylor expansion of these two equations. Suppose this is equation number 1 and this is equation number 2. If we expand it about the DC operating point, so Taylor expansion of the input voltage can be written as this is DC value plus AC value, this is equal to at DC operating point, so this can be written as II V0 about the DC operating point plus first derivative of the function means Vi, so delta Vi delta II, and total instantaneous output voltage is constant plus delta Vi by, and II is constant, delta V0. For small signal operation, transistor behave as a linear. Linear means slope of the characteristic will be constant. Slope of the characteristic constant means first order derivative will be constant. So higher order terms can be neglected. This will be cancelled. This is the DC value, and it is function of the DC current and DC voltage, so they are cancelled, and Vi equal to delta Vi by delta II at constant output voltage, change in total instantaneous current. Actually, the DC biasing voltage is DC value is very, very higher than the AC value. So the change in the total instantaneous value can be considered as just the instantaneous value of the AC current. So change in the total instantaneous means just the AC value, because it is very, very smaller than the DC value. So the change in instantaneous value can be written as just the AC value, and similarly delta Vi by delta V0 II. Okay, so this is equation number 3. Similarly, if we write in the position of the Vi, then we will get the Taylor expansion of this equation. So Taylor expansion of equation 2 directly can be written as AC equal to, just we write in the position of the Vi is IO. So delta IO by delta II for VO II plus delta IO plus delta V0 plus II into V0. This is another equation, equation number 4. Okay. From equation 3, we can write Vi is equal to Hi II plus this is HR V0. Okay, and from this equation we can write IO is equal to this is HF II plus this is HO V0. This is equation number 5 and this is equation number 6. That is HI equal to, HI mean this, and this is delta Vi by delta II. Okay, this is the change in the voltage to the change in current. Change in voltage to the current means impedance, and this is input voltage by input current. So this is the input impedance. Okay, input impedance when output voltage is constant. This is the total instantaneous output voltage. Total instantaneous output voltage mean this is DC voltage, capital letter capital subscript plus small letter small subscript AC value. So this is constant. We know that DC always constant. So only changing parameter is the AC parameter. So it will be constant when AC terms will be constant. So it constant means V0 is equal to 0. What will be the when V0 is equal to 0? Then if we choose the value of V0 in the equation 5, what will we get? If V0 is equal to 0, then this time will be 0. So the HI equal to Vi by II. So Vi by II when V0 is equal to 0. So it is called input impedance when output AC output is 0, when output is short to AC. When output is short, then the voltage will be 0. Input impedance when output is short to AC signal. Okay. Again, from the second terms, this is HR. HR equal to delta Vi by delta V0 when input current is constant. This is the ratio of the input voltage by output voltage. We know output voltage by input voltage means the voltage gain, but here the V1 by V0. So it is called the reverse voltage gain. Okay. And when the input current, instantaneous value of the input current is constant, it constant means the instantaneous the AC current is 0, then it will be constant. So when II is equal to 0 means this part will be 0. II is equal to 0 means this part is equal to 0. So HR is equal to Vi by V0 when AI is equal to 0. So this is the reverse voltage gain. Reverse voltage gain when input current will be 0, when input is open for AC signal. So this is the reverse voltage gain. Now from the equation 6, this is HF. This is HF. So this is delta IO by delta II, and this is constant. This is the ratio of the output current to the input current. Output current to the input current means current gain. Okay, and this is forward current gain. When this is constant, it constant means AC output is 0. So AC output is 0 means this term will be 0. So this term will be 0 means HF equal to IO by II, and AC term is equal to 0. So this is forward current gain, forward current gain when output is short to AC. When VG is equal to 0 means output is short. When I is equal to 0, when input is open. Now another terms, this is HO, and this is delta I0 by delta V0, delta I0 by delta. This is the ratio of the current to the voltage. Current to the voltage means inverse of the resistance, impedance, that means the admittance. II is equal to constant. II equal to constant means AC term is 0. So first term will be 0. So first term 0 means A0 is equal to I0 by V0. So this is I0 by V0 when II is equal to 0. So this is the output admittance when input is open to AC. So these are the hybrid parameters, and why they are called hybrid? Because they are alike in dimension. Dimension of the parameters are not same. So these are called the hybrid parameters. Okay. And these parameters we can easily determine from the static output characteristic, and also the parameters give the real value in the audio frequency range of the AC input signal, and manufacturer easily supply these parameters. So the analysis of the transistor amplifier using hybrid parameter model is very advantageous. Okay, so we always refer the hybrid parameter model for the analysis of the small signal transistor amplifier. Okay, now I will try to draw a two circuit from these two equations. Let's see first equation 5. This is a voltage, so this is the equation of the voltage. Okay, and this is the resistance. This is the current. So it must be impedance. Impedance means the unit of resistance. So this will be the impedance. This is input impedance. But here this is the equation of the voltage. But already there is voltage. So it must be dimensionless. So this is constant. That means the voltage is multiplied some constant, means there is a voltage source. Okay. So from this equation 5 we can draw a circuit. This is input impedance, and there is a voltage source. So this is the input impedance, input voltage, and this is input current, and this is, so part of the VI drop here, and this is HR V0, plus minus. So this is the circuit diagram from this equation. Now from the equation 5 we also can draw, actually here I0 divided into two parts. This equation also can be written as HF II and V0 by 1 by HOE. 1 by HOE, it will be the impedance. So voltage by impedance, that means it will be the current. And since this is the equation of the current, and here already there is a current, so it must be a constant, and so there is a current source. Okay. So the current, this is 1 by I0 current divided in two paths. This is one path and there is a current source, and current source of value II, and if there is a voltage VI, and this is the impedance 1 by HOE. So the voltage across 1 by HOE V0, so the current through this path will be V0 by 1 HO. So there are two circuits from these two equations, and if we connect, then this will be the hybrid parameter equivalent circuit for a transistor. Okay, and if we choose the SIP mode of transistor, then just I will change the, sorry, this is HI, input impedance HI to a HIE, corresponding to the common emitter mode, corresponding to the common collector mode, this will be HIC, corresponding to the common base HIB. But for all the mode of circuit, the hybrid parameter equivalent circuit will be same. Just I will change the parameter. For each common emitter mode, HI will be HIE, and it will be HRE reverse voltage gain for the common emitter mode. This is forward current gain for common emitter mode, and this is admittance for common emitter mode. So these are the parameters for common emitter mode, and we know for common emitter mode the input current is base current. So this is the hybrid parameter equivalent circuit for common emitter mode. So this is the emitter, this is base, and this is collector. Okay, thank you. Next class I will discuss the different performance quantities of a transistor amplifier in different mode of connection using this hybrid parameter equivalent circuit. Okay.